Hello everyone, in this video I'm going to solve a problem about a multiple unit process. But first let me tell you briefly about the multiple unit processes. Multiple unit processes means that we have a process which includes more than one unit or more than one system, which means that we can have an absorber, mixer and splitter in the same process working together. So for solving problems for a multiple unit process, we have to know the concepts of degree freedom analysis and the material balance for these processes. So, and for your information, the industrial processes rarely involve only one process unit. So it's important to know how to deal with these kind of problems. So let's start with our problem by reading it. It says that fresh feed stream flowing at 100 kilogram per hour containing 20% by weight KNO3, which is potassium nitrate, we will represent it as K, and H2O, W. The fresh feed stream is combined with a recycled stream. So from this word combined, we can know that there is a mixer here and is fed to an evaporator. The concentrated liquid solution exited the evaporator contains 50% KNO3 is fed to a crystallizer. The crystals obtained from the crystallizer are 96% KNO3 and 4% water. The liquid from the crystallizer constitutes the recycled stream and contains 0.6 kilogram KNO3 per 1 kilogram of H2O. So we can conclude here that there is a relation. So what they want from us is calculating all stream flow rate values and compositions. To start solving this problem, we have to draw the system to make it clear and easier for solving. So we'll start from the beginning. Fresh feed stream flowing at 100 kilogram per hour. So there is a stream here, which is the fresh feed stream. Okay, it's 100 kilogram per hour. Okay, containing 20% by weight KNO3 and H2O, which means that KNO3 is 20% of K. Okay, and the rest, which is 100 minus 20, it's 80 for W, which is the water. Okay, where it goes, before it's entering the evaporator, they said that is combined with a recycled stream. So there's a mixer here. Let's draw the mixer. It's like combined with a mixer with a recycled. So there's a stream here coming from the recycled stream, and there's the mixed stream is entering the evaporator. So we will draw the evaporator here. Okay, we can write evaporator, and this is the mixer, of course. So the evaporator, there is a feed coming out from the evaporator, and of course the work of the evaporator, we all know that it evaporates a pure water. So there is a water here, we can write pure water. So let's complete. The concentrated liquid solution exited the evaporator contains 50% KNO3 here we can write 50% of K, and the rest of course will be water, so it's 50% W. Okay, so this stream is entering the crystallizer. So we will draw the crystallizer here, as it's like, you can draw any shape of course, but I'm drawing different shapes to make things clear. So there is a feed. The crystals obtained from the crystallizer are 96% KNO3. So there's a stream here which contains 96% of K, and of course the rest are water, which is 4% of water. So the liquid from the crystallizer constitutes the recycled stream and contains 0.6 kg KNO3 per 1 kg of H2O. So the recycled stream is coming here. So this is the crystallizer. And for making things more clear, we are going to put numbers for the streams. So this is M1, and I mean by M, it's the mass flow rate. So this is M1, this is M2 here, we can name this M3, this one is M4, the recycled stream is M5, and finally this is M6. Of course this is the recycle, and we know that for every stream there is a concentration, compositions. So we know the M1, the compositions for it, and M3 and M4, but the M2 we can write that K is equal to, the composition of K is equal to X K2. We can name it as, because it's an unknown. And for water is 1 minus X K2. Okay, and for M5 we can write K as X K5, and W is 1 minus X K5. So this is the complete system here, and we can start calculating the degree of freedom, then solving the whole process. So after drawing the whole process, the second step is doing the degree of freedom analysis to know which system we should start solving with it. For making things more easier, I'll make borders for each system to know the number of unknowns and the number of independent equations and the number of relation to conclude the number of degree of freedom. So I'll start with the mixer. We can make borders like it's like this to know which streams are entering or going out from this system. The second is the evaporator. It's like this. And the third one is the crystallizer. And finally, we have to make a border for the whole process. So we will make like this. Of course, the recycled stream, it's not crossing the border of the entire process, because it's only between the crystallizer and the mixer. Of course, the pure water is crossing the whole process border. So to calculate the degree of freedom, I will draw a table. We have number of unknowns and number of independent equations and number of relations. We have in each system. Finally, it's the number of degree of freedom. We will represent it as NDF. Okay, so it's a table like so for the evaporator, the crystallizer, the mixer, and finally the whole process. Okay, so number of unknowns for the evaporator, if we calculate it, is we have M6, it's unknown, M3, this is going out from the system, and entering the system is M2, so it's 1, 2, 3, and the X here, so it's 4 unknowns. We will write here 4. The number of independent equations depends on the number of components in this system. So the only components we have is K and W, so it's 2. The number of relations, there's no relation inside the evaporator, so it's 0. For the crystallizer, the number of unknowns is, we have here M3, so it's 1, 2, M5 is the third one, and X for the composition. So it's 1, 2, 3, 4. We will write here 4. The number of independent equations is the same as the evaporator. And actually it's the same for the mixer and process, of course. So we will write 2 and 2. The relation for the crystallizer, as I told you before in the question, there is a relation in the recycle. So there is a one relation here. The mixer, the number of unknowns we have, of course M1 is 100 kilograms, so we know it. We have M2, M5 entering the mixer, and X for K2 and X for K5. So they are 1, 2, 3, 4. So they are 4. And here's 2. And there is 0 relation here in the mixer. For the process, we have M4 and M6. They are the only unknowns in the process, because of course we know M1. So they are 2. The relations are 0. So how to calculate the number of degree of freedom? We do like 4 minus 2 will give us 2. 4 minus 2, it's 2, and 2 minus 1 is 1. 4 minus 2 is 1. Sorry, it's 2. And 2 minus 2 is 0. So the lowest number of degree of freedom is for the entire process. Accordingly, we start with the overall process system. We start solving with it. The third step after calculating the degree of freedom is the calculations. So as I said, I'll start with the system overall because it has the lowest number degree of freedom. So overall, I'll get used from the relation in the recycle stream. We can start solving. The relation said that the recycle stream contains 0.6 kilogram of KNO3 per 1 kilogram of water. So I'll write it as X. We can get use from it to find the composition of K in stream M5. So X of K5 equal to 0.6 kilogram of K over 1 plus, of course this is kilogram of water, plus 0.6 kilogram of K. The reason that I wrote that because the composition is equal to the mass of the component over the all components mass, or the sum of the masses for all components. So it's equal to 0.375. And from this number we can find W, the composition of the water. So it's 1 minus 0.375, which is 0.625. After finding these numbers, I'll do the material balance for the overall system. It's like writing the mass flow rates, entering the process and going outside from the process. So M1 is entering the overall process, the overall system, and it's going out, the streams that are going out is M6 and M4. So M1 is equal M6 plus M4. Of course, we know M1 equal 100 kilogram per hour, and we have to find M6 and M4. Okay, how can we do that? We can do it from component balance. So the component balance is like, so it's component balance okay, it's like doing the balance for each component. So I'll start with K. K and M1, it's 20%, which is 0.2 multiplying by 100, which is the value of M1, equal, because of course M6 is only pure water, so it's the K in M6 is 0, the composition of K, and in M4 it's already known, which is 96. Okay, so it's 0.96 multiplying by M4. So from this equation we can find M4, which is equal to 20.83 kilogram per hour. Okay, and from M4 that we find it, we can find M6 and this from this equation. So M6 equal to 79.17 kilogram per hour. After calculating some unknowns from the overall process, we can go back to the number degree of freedom for the other processes and doing it again and see which process we can start with it next. So I decided to start with the crystallizer. So process crystallizer. I'll start with the total material balance, of course. It's M3, which is entering the crystallizer as we see. M3 equal to M4 plus M5. So M3 equal to M4 plus M5. Okay, so M4 is already known from the previous system. So M4 equal to 20.83. I will do the component balance as the previous system. And I'll do it for K. So an M3 K is equal to 50%, so it's 0.5. So 0.5 multiplying by M3 equal to 0.96 multiplying by M4, which is 20.83, plus an M5. We know that K, the composition of K, is 0.375. Of course, multiplying by M5. From this equation, substitute M3. It's like M3 equal to 20.83 plus M5. So 0.5 multiplying by this, which is 20.83 plus M5, equal to 0.96. 20.83 plus 0.375 multiplying by M5. Solving for M5, we can write it as, of course, the only unknown in this equation is M5. So, sorry, we can calculate the value of M5. It will give us 76.65 kilogram per hour. So from M5 here, we can find M3. So M3 equal to 20.83 plus 76.65, which is equal to 97.48 kilogram per hour. The last system that I will solve is the mixer. Of course, we will not have to solve for the evaporator because we will already, after finishing solving the mixer, we will know all the unknowns. So, starting with the mixer, of course, I will start as I did with the material balance. So it's M1 entering the mixer, as we can see here, and M5. So we have two streams entering the system, M1 plus M5 equal to M2. So M1 and M5 are knowns. So M1 is equal 100 kilogram per hour plus M5, which is 76.65 kilogram per hour. We can easily find M2 now, which is equal to 176.68 kilogram per hour. Now, doing the component balance for K, for K, 20 kilogram, of course 0.2 multiplying by 100 for M1, which is 20 kilogram per hour, plus for M5, the composition of K is 0.375 multiplying by the mass of stream 5, which is 76.65, equal to the composition of K and M2, which is unknown, and we will find it xk2 is multiplying by the mass stream here is 176.68, of course, kilogram per hour. So xk2, we can find it easily now. It's xk2 equal to 0.276. And for finding the composition of water, we can just easily doing 1 minus 0.276. That's it, and thank you for watching.